tell you a story tonight about something mathematical. And if you hang out with mathematicians enough, you will find that we use this word, story, to describe mathematical concepts. So we want to know the premise, we want to know the relationships to each other, and things like that. I have a partner who studies story theory and writes sometimes, and he took issue with this word sometimes before, but I think he's come around. So I'm going to tell you, this story about infinity. But first, I'm going to tell you how I came around to thinking about this. So it starts when I'm 17 years old, at the prime of loathing mathematics, because I'm a 17-year-old girl, right? And I'm hanging out at my friend Chris's house, who's home over summer break. From college, right? Okay. Yeah, where he is studying math himself. And we're doing what we do often, which is staying up until the wee hours of the morning watching really fucked up movies. So we have just gotten through some David Lynch nonsense, and my brain is feeling particularly pliable. So I ask him in a moment of weakness, so you study math. What's that like? What's that about? And he answers me with, well, what do you know about infinity? David Lynch just fucked up my mind, and he wants to know what I know about infinity, right? Okay, so he proceeds to tell me the story that I'm going to tell you tonight about the various sizes of infinity. And once he gets through, I'm hooked. This is amazing. This is what math is? Seriously? So, once it comes my turn, I graduate from high school, I follow this guy off to the same university to study math myself. I get a bachelor's degree, I follow it up immediately with a master's degree and a PhD, and a few postdocs off in the world, and finally I land here as a professor at City College of New York. But right before here, just before this, I'm down in Australia as a postdoc at the University of Melbourne, and I'm sitting in a pub with a few of my colleagues, because that's what we do. We wander off to the outskirts of the world and hang out with like-minded lunatics and talk over a pint or two. And what's happening at this pub this night is something a little bit like this. It's called Laborastory. People are getting up and talking about various scientists' lives. And somebody gets up and starts talking about Georg Cantor and his work with infinity. Now, this is the exact same work that I had heard about when I was 17 years old from my friend, but he wasn't talking about the work specifically, he was talking about how it was received at the time. As you might guess, not very well. Henri Poincaré, phenomenal mathematician, famous to this day, called his work a grave mathematical malady, right? Grave mathematical malady. Leopold Kronecker calls him a charlatan and a corruptor of youth. This is why I'm telling you this. Corruptor of youth, I lost my shit, right? Corrupting youth. Good old Cantor, 80 years after his death, corrupting youth into studying mathematics. All right, so what is infinity? When you start to think about infinite things, stuff that comes to mind actually turns out to be mostly physical. It's, the infinite expanses of the universe, the infinite possibilities of a moment. The problem is that most things that you think about as infinite are measurable. One of my favorite things on the internet is this cosmic eye project. It starts with this woman's face, and it starts to zoom out. If I can get it to play. No, that's not play. Ah, there it goes. It starts to zoom out, and out, and out. Right, and if you watch the bottom of the screen, it has a scale, right? A kilometer, 10 kilometers, very hypnotic. You could watch this for a while, right? Maybe I should just stop talking and we could watch this video. Right, anyhow, I bring this up because it's putting into perspective what we think of as infinite. Turns out that just really, really big is not the same as infinite. Most things that are really, really big are measurable, and if you can measure it, it's finite. The distance to the outer galaxies is finite. The distance to the edge of the universe is finite. So when you think about infinity, a lot of your biases are based in physical intuition, and the point is, physical intuition betrays you every time. Infinity is a theoretical concept. It is a very useful theoretical concept. Modeling things as basically infinite is good. But when you start to compare things that are infinite, it's by nature a thought experiment. Okay? So some of these things are going to bend your physical intuition, and that's okay. That's good. That's where we get into math instead of physics. Okay, so let's start with counting. Happy Groundhog's Day, right? Got a couple groundhogs here for you. How many groundhogs are there on the screen? Three. 1, 2, 3. And the way you do it is you match up the numbers 1, 2, and 3 with the 3 groundhogs. Every groundhog gets a number. Every number gets a groundhog. This is counting. If you have more groundhogs, more numbers, great. More groundhogs, more numbers. You'll never run out of counting numbers because the counting numbers themselves are infinite, even though you only use a finite number of them at a time. Okay, so you only use a finite number at a time, but you know that they'll be there for you as you get more and more and more groundhogs. So instead, let's pretend that we have an infinite number of groundhogs. 1 for every counting number, right? Phil doesn't know if this thing is going to end or not. All right, so that's the same thing as taking those groundhogs and lining them up as a list. So first groundhog goes to the first item on the list, second groundhog goes to the second item on the list, and so on. This is what we call countably infinite. Countably infinite means capable of being lined up 1 to 1 with the counting numbers. All right, so our first example of a countably infinite set, the counting numbers. Counting numbers can be lined up 1 to 1 with themselves, 1 to 1, 2 to 2, 3 to 3, and so on. Well, what if 3 more groundhogs show up to the party and they want to hang out, right? Is countably infinite plus 3 still countably infinite? Well, sure, I can ask all of those groundhogs, the yellow groundhogs over there, everybody move down 3, make room for the new guys. And since the counting numbers don't run out, I can say, hey, 1, could you move to 4? And 2, could you move to 5? And 3, could you move to 6? And so on. And I could make room for those 3 new groundhogs. 9 more groundhogs show up. Sure, everybody move down 9. We're fine. So the set of integers from any fixed number and above is countably infinite, because you just start counting from the bottom, and you go, and you go, and you go. Line up 1 to 1 as a list. What about all of the integers? So I don't have a good starting place to just count up and up and up with all of the integers, because they expand infinitely in both directions. Well, I'm going to play a similar game. I'm going to start with my original list. There's my countably infinite number of groundhogs. And I'm going to bring in the rest of them. I've got 0, -1, -2, and so on all the way down the line. Now, I can't ask, hey, 1, could you move all the way down to infinity? Because infinity isn't a number, okay? There's no infinity point on the list. I have to tell 1 physically, where do you go? So instead, I'm going to ask everybody to move down so that they have 1 space in between them, you know? Make sure that you have a chair in between you and your neighbor so you aren't cheating off of each other's tests or whatever. Okay, so I'm going to ask number 1, could you move to 2? And 2, could you move to 4? And 3, could you move to 6? So all of the yellow groundhogs get matched with twice their number. And then I'm going to take the purple groundhogs and I'm going to shuffle them in. Everybody take up a vacant spot. So 0 goes to 1, -1 goes to 3, and so on. The even items on the list get positive groundhogs. The odd items on the list get everybody else. And you should ask yourself before you move on too far, did I really get everybody? And you can do that by saying, all right, no matter what groundhog I ask you, where could you find it? You'll be able to answer that question. So the yellow groundhogs got asked to move down to their double. So where would I find 121? 242, beautiful. The negative groundhogs got put right below their positive counterpart. So -53 is right below positive 53. Positive 53 went to 106, so -53 is at 107. Very good, awesome. So yeah, we got them all. We can answer this question no matter which groundhog we're asking. So yes, we got everything. Every moment on the list is taken and every groundhog has a place. Fantastic. So the counting numbers and the integers are both countably infinite. let's talk about a slightly different kind of example, the rational numbers. So the rational numbers are the fractions. You take an integer divided by an integer, 2/5, -17/3, 0/1 is otherwise known as 0. Okay, and I want to know can I list them? The answer is yes, but it doesn't work the same way as before. The problem is the rational numbers are really crowded. In between every pair of fractions, you can always find another fraction. No matter how far you zoom in, you can always find a fraction in between. The rational numbers are what we call dense, meaning that they're crowded to be able to talk about the next one. There's never a next rational number. Okay, so I can't list them in order of size anymore. I can't even do this kind of alternating thing. But I can expand my mind off into 2 dimensions and make myself a table of rational numbers. So here's a table of the positive rational numbers. You have the rows correspond to the denominators and the columns correspond to the numerators. So if I go to the 5th column and the 3rd row, I get 5/3 and so on. Now, if you're quick, you see I've actually over-listed the rational numbers. There are a lot of these that aren't in lowest form, meaning 2 divided by 2 is the same thing as 1, which I already have on my list somewhere else, or 4/6 is the same thing as 2/3. So I'm going to go ahead and cross all of those out. And now, since we're back in kindergarten learning how to count, let's move on to coloring. I'm going to start in the upper left-hand corner and color this table in, zigzag across. And I'm going to be able to get everywhere in the table by coloring in, by doing bigger and bigger zigzags. What do I mean by that? It means I'm going to start counting from the upper left-hand corner and proceed up and back and forth along diagonals, skipping the grayed out things, counting them one at a time. And in this way, I can count all of the rational numbers using the positive integers. So the rational numbers, even though I can't list them in order of size, I can still list them. So our 5th example, the positive rational numbers are countably infinite. Whew, all right. So you should be asking yourself at this point, is there anything that is infinite but not countable? Answer is yes, okay? Because otherwise, why would we call it countably infinite, right? We just call it infinite. So the answer is yes. So let's get up one more step up to the real numbers. This is a stupid name, but real numbers are things that you get by looking at the real number line. So think about an integer with an infinite decimal expansion. So 1.00000 repeated is the same thing as 1. That's okay. Negative 2.12121212, anything that has a repeating decimal expansion turns out to be rational. Or you have things like 3.14159 and so on, which we know is pi, which is an irrational number. You can't be expressed as a fraction. So the real numbers include the integers, they include the rational numbers. They don't include things like square root of -1, which is a complex number, very useful, but not in the real numbers. And our goal is going to be to understand why the real numbers aren't listable, aren't countable. So how could we do it? Well, first of all, we should understand, what does it mean for 2 real numbers to be the same or different? What does equals mean? Okay, so if I take a real number, infinite decimal expansion, and if I pick just 1 digit or more, but at least 1 digit, and I change it, I get a new number, right? So 2 numbers are different when they differ in at least 1 decimal place. There's some 0.9 repeating technicalities there, but I won't bore you with them. Okay, so countably infinite was capable of being listed. So our job is to show that this is incapable of being listed, which means that no matter how much coffee you had this morning, no matter how many good ideas you have, if you tried to make a list of the real numbers, you would fail. How do you know that you fail? By finding a real number that you missed. So our goal is to show that no matter what list you make of the real numbers, you're missing something. Okay, so we can start with any list of real numbers. Here's an example, just so we have something to work with. And we're going to build a number that's missing from that list. And the way I'm going to do it is I'm going to do it 1 decimal place at a time. So I'm going to mark the decimal places of my infinite list. I'm going to mark the first decimal place of the first number, the second decimal place of the second number, and so on down the way. And I'm going to start building my new number that's not on this list, one decimal place at a time, by looking at the first number, asking what its first digit is, and changing it. So 3, I'm going to change it to a 0. So my number is obviously not the first number on the list because they don't match in the first decimal place. Second number, second decimal place, my second decimal place is going to be different. So my number is different than the second number. Third number, third decimal place, I'm going to pick a 1 because that was a 0. So my number is different. And all the way down the line, 3, I'll turn into a 0, 0, I'll turn into a 1, and so on. And since the list items are labeled by natural numbers or counting numbers, and the digits are labeled by counting numbers, I will never run out of possibilities. I can tweak them one digit at a time. This is different from rational numbers because rational numbers eventually have to find a pattern, whereas real numbers can do anything they want. Even if I added that number to my list, I could still go through and build a new number that's not on my list. So no matter what list I start with, I can build a new number that's real, that's missing. So any list of real numbers is incomplete because you can find something missing, which means that the real numbers are not countable. This was the huge breakthrough of Cantor. This was the thing that got him called a charlatan and a corruptor of youth. This was his diagonal argument showing, no, there are things that are bigger than the integers. Infinity is not a well-defined term. All right, so let's summarize. We started with finite things. We could count. Then we got countably infinite, like the positive counting numbers. And then we found out that there's a whole new kind of infinity. It's bigger and better. It's called the size of the real numbers, uncountably infinite. Are we done? Is there more? Right? Are there 2 infinities or are there more? Well, it turns out that there are. If you take sets of real numbers, like 3 and 5, or 3 and 5 and 7, or 3 and 5 and 7 and pi, right? And you take all possible sets of numbers, and you take that set. Just like people in a city, and now cities in a state, or states in a country, right? I'm going to take sets of sets. The number of sets of real numbers is fundamentally bigger than the set of real numbers, okay? That you can't match them up one to one. I can do it again. I can take sets of those, and sets of those, and sets of those, and sets of those, and they get bigger and bigger and bigger and bigger. So we give these things names. These are called the alephs. Aleph 1 is the size of the real numbers. Aleph 2 is the size of the sets of real numbers, and so on down the line. Aleph naught or Aleph null, or Aleph 0 is the size of the counting numbers. So we have countably infinite number of sizes of infinity. Okay. Are there more? Right? That's the mathematician, right? More? This is where it gets real weird. Set theorists kind of go off the rails at this point. So put it again. There are at least countably infinite numbers of sizes of infinity. Question, are there more? Well, Cantor, the guy who revolutionized this field, thought no, there can't be more, right? He worked on it for a long time trying to prove that there couldn't be more. It's hard to prove the lack of existence of something. It's easy to prove the existence by saying, look, I found it, right? But if you're trying to say you have no hope of finding this thing, that's hard, and he tried for a long time. 30 years later, Hilbert comes along and lists the most important problems of the 20th century, and this was top amongst them. Can we figure out, are there more sizes of infinity? Finally, 1940, Gödel, along with lots of other things, says, okay, he proves that you can't disprove the other sizes of infinity exist. So maybe they're out there. Nah, you can't do that either. Finally, we prove that, okay, it's all right. You can't prove that they exist either. So you can't come up with an example because that would prove that it was there, right? Look, I found it. No, you can't prove that they're there either. So this is what's called the independence of the continuum hypothesis, if you're looking these things up on your own. All right. So I will leave you that, but before they sing me off the stage, just a few more things if you want to follow up on this and learn about this more. There's a great thought experiment called Hilbert's Grand Hotel, and there's a good video online called the Infinite Hotel Paradox that goes through it. You can also go to Vi Hart's YouTube station that has lots of really great math videos, and she has a few on infinity. Or you can go read my friend Jordan Ellenberg's book on how not to be wrong. It's a fantastic book. The last chapter is on this kind of challenge of looking through the set theory axioms at large. So thank you very much. You've been a great audience.
Go to nerdnite.com to find a Nerd Night event near you. And don't forget to subscribe to our channel for our latest presentation.